Hello, this is our MSE 4791 project with the Laminator. I am Brendan Miles, helping along with this project were Michael Rupanen, Kerry Haniger, and Mohammed Ben Doman. Beginning with our project parameters, our fixed variable was that we had a high modulus carbon fiber. Our design variables were the type of matrix, the type of laminate, the angle ply, and the fiber volume percentage. Finally, our optimization parameters were thickness, cost, and weight. We made a few base assumptions to start to simplify things in our project. First, the fibers are uniformly distributed throughout the laminate. Perfect bonding between fiber and matrix exists. The matrix is free of voids. Forces are applied parallel or perpendicular to the fiber direction. There are no residual stresses. The fiber and matrix follow linear elastic behavior, and that lamination theory holds. Lamination theory says that the laminate must be thin and wide. Perfect interlaminar bonding must exist. Strain distribution throughout the thickness is linear, and that macroscopic homogeneity and linear elastic behavior is followed. Of these, our laminate most likely did not follow the thin and wide criteria, but I will touch more on that later. Continuing with our assumptions, we settled on a safety factor of 1.4. This was from NASA's literature saying that this was the lowest they would go in aerospace. Next, we assumed that the transverse modulus is 10% of the longitudinal modulus for our fiber. This was based off literature review, specifically with wood. Next, we said that the shear strength of the matrix was equal to the tensile strength of the composite. This is based on two concepts. We took an average to determine material properties as a conservative approach, and shear for metals is commonly estimated as 1/2 tensile strength. Since the shear strength is dominated by the weaker material, it was decided to use the larger value as it better matched values for shear strength in commonly found composite lamina. Finally, we used the Tsai-Hill failure criteria. We chose this criteria because experimentally it was determined to correlate better than the stress or strain failure criteria using an E-glass composite. Furthermore, when we got into actually testing in the laminator, we found that the Tsai-Hill failure criteria was the second most conservative of the 5 failure criteria. This allowed us to be conservative, but not necessarily be too conservative that we would sacrifice weight and thickness. Moving to our process, we began with a balanced and symmetric laminate. We did this because this removes coupling coefficients and it simplifies the problem. So this would eliminate the extension shear coupling in the case of a balanced laminate and the extension bending coupling in a symmetric laminate. Additionally, using a balanced laminate also ensures that there are no coefficients of mutual exclusion between the layers. Next, we began selecting between a phenolic or epoxy resin. We finalized these as our final two options because of research we had done into the industry. We figured that we'd settle with epoxy resin because of the higher strength it provides, and the epoxy is also found to have a lower density. Unfortunately, the epoxy is more expensive, but since this is an aerospace application, the lower density should lead to cost savings over time. Next, we ran fiber volume percent calculations using the micromechanics tool in the laminator to observe the effects of volume fraction on the mechanical properties of the laminate. And from there, we could figure out that the fiber volume fraction was not going to be a driving force for our design. Next, we moved into the angle plies. So of the options we had, we chose 0-90 patterns, 0-45-90 patterns, or 0-30-45-60-90 patterns. Of those, we quickly eliminated the 30-60-90 pattern because the 30 and 60 were failing at way lower values than the 0-90 and 0-45-90. Experimenting. So first we ran into some thickness and software limits. Industry generally has lamina that are 0.6 millimeters thick. However, given the forces we were given and the conditions of our materials, we literally could not fit enough lamina into a laminate that would bear those forces. So using that, we moved up and up and up. We settled on 6 millimeter thickness per layer, but we also tested 2, 3, and 4 millimeters, and we figured out that the thickness of the lamina and the amount of lamina you needed total was linearly scaling. So when using 6 millimeter thickness, you could use less lamina and it would still be just as thick as if you used 2 millimeter thick layers. We settled on 6 just because it would be easy to iterate with those with a smaller amount of layers. Next, we iterated on those patterns of 0 to 90, and we moved upwards in terms of thickness and number of lamina until it was just large enough to withstand our safety factor. Then from there we would lower the fiber density until the threshold was hit again, and we moved forward. We discovered that the 04590 maintained a safety factor at the 50% volume fraction, whereas the 090 patterns would only maintain it at 55% volume fraction. This decrease in weight also decreases costs, so we're moving forward with that with the 04590. As you can see, the cost reduction is 18.2%, and the mass reduction is 3.6%. That's moving from 60% volume fraction to 50% volume fraction in a 04590 pattern. So moving forward, we had two final designs that can be seen on the screen here. And we needed to differentiate them in some way, so we decided on out-of-plane shear stress. Other things that decide out-of-plane shear stress: the first requires coefficients of mutual influence or differences in Poisson's ratio throughout your laminate. However, since we had no coefficients of mutual influence because of our balanced symmetric laminate and no difference in Poisson ratio throughout, we ended up not having to consider that. Next, there's delamination at boundaries. However, there's not enough info provided in the project and not enough capabilities in the Laminator software for us to consider this. Next, we consider that plus and minus theta angle plies should have many interfaces between each other. Technically, none are adjacent in either of the lamina. However, one of them has a small advantage in one extra layer between plus and minus theta layers. Finally, having adjacent 90-degree plies can lead to delamination. Again, neither of these have 90-degree plies, so in conclusion, both designs may be acceptable. However, we did have to finalize that. Before moving into finalization, here's the flowchart of our work. As you can see, we went from choosing the matrix, setting the volume fraction, stacking sequence, then we would iterate those stacking sequences, input loads, materials properties, and material strengths, test each laminate for our failure using that Sci-Hill failure criteria and a factor of safety of 1.4, and then we iterated again through failures and just increase the number of layers. If there's no failure, we decrease the fiber volume fraction until failure, and so we reached the smallest fiber volume fraction possible. This was just done to minimize weight and cost. And then finally, we optimized the angle stacking sequence for best possible load carrying and out-of-plane shear. So the design we picked is on your screen. It is 0, 3, 90, 0, negative 45, 0, 2, 45, 90, 0 symmetric laminate. This design is superior because the 0, negative 45 layers have increased shear and normal stresses, and this laminate divides these two over areas, while the other laminate would put them closer together and concentrate those stresses, which is not good. So moving forward with this design, our final thickness is 132 millimeters. The weight is 7.87 kilograms, and the cost would be $191.37. Unfortunately, this design is likely not feasible due to the lamina thickness and overall thickness. Our laminate ended up being almost as thick as it was wide, which would mean that lamination theory would not hold, which was a big factor in one of our assumptions. This means that this type of composite may not be suited for this application in terms of forces. Additionally, because we had to move to 6 millimeter thick lamina, and most of the industry operates on 0.6 millimeter thick lamina, we figured that composites are probably not the best option here. Thanks, and that's all.